So in this session we are going to discuss about the interpretation of batch reactor data. That's basically we are trying to develop the rate expressions which are further to be used to design the different continuous reactors. So the chapter is interpretation of batch reactor data. Now, how to generate that data? Right. First, what is a batch reactor? No input or output, initial loading with reactant, and it is inherently unsteady. Progressively the concentration changes with time. Generate Ca versus T, that is concentration time data at different temperature. Right. So that is to be generated, the concentration, how it is changing, concentration of the limiting reactant, how it is changing with time. So next question, how to measure the concentration or conversion of the reactant. So there are several procedures. First, direct measurement. Of concentration by appropriate analytical instrument. Second, indirect measurement that is upon measuring the electrical or optical property. Just I do what we do in this spectrophotometer using this Lambert-Beer's law, right. So in spectrophotometer what happens? ln of I0 by I is equal to K into C into L, right. So from there we have got a linear relationship between the ln of I0 by I with respect to C, and we can measure the concentration if we have the calibration curve. From the pressure data in constant volume, gas phase reaction, we will discuss it, how it can be performed. And lastly, from volume data in a constant pressure system, reacting system. So these are the different ways of measuring the concentration or concentration equivalent term, right. Next, how to analyze the kinetic data. There are two approaches. First is known as differential analysis. In differential analysis, from CA versus T data, generate minus RA versus CA data. Right. Now, minus RA as minus RA is in the order of minus dCA dt, we have to use numerical differentiation. Maybe this is prone to large errors. And this numerical differentiation needs a large number of data points. Right, that's a disadvantage. However, what is the advantage? We can directly formulate the rate equation or rate expression without any repeated trial, right, which is the typical characteristics of the second method, that is the integral analysis. Here we have to assume a model, a kinetic model, generate the final form of CA as a function of t and convert the function to a linear form. Go for the straight line fit and check the validity of the model. You have to check the validity of the model, right? So this is advantage requires less number of data points. Number one. Disadvantage, this is based on repeated trial. Right. So that's the overall idea about, or outline rather, that how to interpret this batch reactor data. That how we can interpret this batch reactor data. This is a typical outline, right? And based on that, we will next proceed for this analysis. First, we will consider a constant volume system. So, first it is a constant volume system. Right. Now, in a constant volume system, pressure changes. Pressure, we represent it in terms of pi, changes with time, with the progress of the reaction rather. So, from this pressure recording, we can actually get the concentration or the partial pressure term. And you see that we may use partial pressures of components to represents the equivalent data, that is equivalent to CA versus T. Right. So, so total pressure data. So, here it is total pressure data and its use. How we can get this partial pressure from the total pressure data, provided we know the stoichiometry of this system. So, AA plus BB giving RR plus SS, then etc. Now, at time t equal to 0, let us say the number of moles of A is Na0, this is Nb0, Nr0, Ns0 and N total number of moles. Right. Now, for t greater than 0, let us say this is Na0 minus A into X. X is the amount of moles, or Ax is the amount of moles of A that has reacted. So, for B it is Nb0 minus Bx. This is Nr0 plus Rx, Ns0 plus Sx, and this N0, this is N, which is Na0 minus Ax plus Nb0 minus Bx plus Nr0 plus Rx plus Ns0 plus Sx. So, this we can write as N0 plus R plus S plus dot dot minus A minus B dot dot into X. So, this is N0 plus delta N into X, where delta N is R plus S product stoichiometric coefficient minus sum of the reaction stoichiometric coefficient. Right. Now, PA equal to N0 minus Ax divided by V into RT. Right. Yeah. So, PA by RT, PA equal to N0 by V by RT minus A into X divided by V by RT. Now, no, not N0, this is Na0. Now, here you see Na0 by V into RT is obviously PA0 minus X. How we can write? X we can write as A by V, A by V, N minus N0 by delta N. N minus N0 by delta N into RT. So, this is PA0 minus A by delta n minus n0 RT by V. Volume remains constant. So, it is PA0 minus A by delta n into pi minus pi 0. Pi is the pressure at time t, whereas pi 0 is the initial pressure. So, this is PA. Similarly, you see you can write PR is equal to PR0 plus small r by delta n into pi minus pi 0. Right? So, if here from the conclusion is, if we have recorded pi versus t data, we can generate PA versus T, provided we know the stoichiometry of the reaction. Right. So, just what I have stated, that we can measure the concentration by measuring the pressure in a constant volume system. So, we can do that using this equation. Next, instead of writing the concentration, it is better to write the conversion, which is a dimensionless form, right. Fractional conversion or conversion. So, fractional conversion will give you the idea x a, say it is for a, and that is equal to Na0 minus Na by RT. A is being considered as a reactant. So, for constant volume system, this is divided by Na0. So, here we can write that Na equal to Na0 1 minus Xa. So, we divide this side by volume. So, we get Ca, because Na by V as volume remains constant is a concentration, and Ca naught is the initial concentration 1 minus Xa. So, obviously dCa with a minus sign equal to Ca naught into dx. So, with that basic understanding of constant volume systems, how to represent the concentration and how to convert the total pressure data to the partial pressure, and partial pressure can be further changed into conversion, right. So, conversion of the is independent of the fact that whether I am using the partial pressure or concentration. So, Pa is also equal to Pa naught into 1 minus Xa for constant volume, and dPa is equal to minus of Pa naught into dxa. So, with that basics, let us go for integral method of analysis, where we have to do a lot of algebra. So, integral method of analysis. So, this is constant volume system. So, first is a first order reaction. A giving product and the rate constant is K. So, the rate expression, we assume, let us say it is a first order reaction. So, what will be the concentration versus time plot? So, that is the objective. So, this is minus of dCA dt is equal to Ca naught into dxa dt. dCA minus of dCA is equal to Ca naught into dXA, and that's equal to K into Ca because it is a first order. So it is K into Ca naught into 1 minus Xa. Right. So dXA dt Ca naught cancels out from both sides, K into 1 minus Xa, and upon integration log of 1 minus Xa equal to K into T. Right. So how do you check that whether this model is valid or not? Say we have generated this T into T versus Ca data. These are experimental data. Right. So as it is constant volume, we can calculate Xa as Ca naught minus Ca divided by Ca naught. So Xa 0, so we can generate this, right. So finally we will have minus of 1 minus ln of 1 minus Xa. So Xa is 0, ln is 1, ln 1 is 0. So in this way we can generate that. And we will plot this data as minus of ln 1 minus Xa versus T, and if say these are the scatter plots, if it is a first order, it must be given, the best fit line must be a straight line passing through the origin. So if we have high R square of the linear fit, then it confirms the first order kinetics. Right. So for this sort of reaction, we have the specific equation. Note, if we have a first order reaction, minus Ra, say it's equal to K into Ca to the power 0.6 into Cb to the power 0.4, right. So also first order reaction, also a first order reaction, but the rate kinetics does not corroborate with the previous rate expression, because the stoichiometry was totally different, right. So though it is overall order is first order, but it's a bimolecular reaction, A and B giving some product. So it will not corroborate with this minus of ln 1 minus Xa versus T to be a straight line passing through the origin, because here the stoichiometry and there the stoichiometry is different, right. So that's the first order's integrated form. So next go for second order's form. Second order bimolecular reaction. There is A plus B giving product. C, A plus B giving product. So minus Ra equal to K into Ca into Cb. So it is K into Ca naught into 1 minus Xa into Cb naught minus Ca naught into Xa. Why? Because here you see the 1 mole of A reacts with 1 mole of B. So if Ca naught into Xa moles of A has reacted, definitely Ca naught into Xa moles of B must react. So present concentration of B is the initial concentration of B minus the amount of B that has reacted. So, taking this Ca naught common, here 1 minus Xa and here we will have M minus Xa, where M is equal to Cb naught by Ca naught. So, thing is that next we have to integrate it. So, this is minus of Ca naught dxa dt plus this Ca naught and this square cancels out. So, dxa divided by 1 minus Xa into M minus Xa equal to k into Ca naught into t, and here the integration will be 0 to Xa. So, you see that 1 divided by M minus Xa minus 1 divided by 1 minus Xa, this is 1 minus Xa minus M plus Xa. So, 1 divided by 1 minus M, integration 0 to Xa dxa equal to k Ca naught t. So, we will have 1 by M minus 1 minus M. So, minus of ln M minus Xa 0 to Xa minus of ln 1 minus Xa 0 to Xa is equal to k Ca naught t. So, this will be plus, right? So, if I take this minus common, so 1 divided by M minus 1, 1 divided by M minus 1 into ln M minus Xa upper limit, lower limit M, right, because Xa is 0, and minus 1 minus Xa, the lower limit is 0 because it is ln 1 equal to k Ca naught t. So, we have ln of M minus Xa divided by M into 1 minus Xa equal to k into M minus 1 into Ca naught into t. So, this is the integrated form. So, what we will do? We will generate this t, Xa, then M minus Xa, then 1 minus Xa, then ln of M minus Xa versus M into 1 minus Xa, that data. Once we generate it, so we will plot that ln M into M minus Xa, M 1 minus Xa versus t, and if I have a straight line passing through the origin with high r square, right, greater than say 0.95, it must corroborate to the second order kinetics. So, from this slope, you see, slope is equal to k into M minus 1. So, if it giving you a fit of straight line, linear fit, a straight line with high r square, then you can confirm that this is a second order reaction, bimolecular second order reaction, and we can get the k value from the slope measurement, provided we know the value of M. Obviously, we have to know the value of M, otherwise we cannot plot this. Now, you see that minus of Ra, there is a note we have to understand, minus of Ra equal to k Ca Cb. If Cb naught is much higher than Ca naught, then what will happen? We can approximate it as k prime into Ca, where k prime is equal to Cb naught into k. So, this sort of reaction is called pseudo first order kinetics. Right. A second order reaction can be approximated to a first order if I am setting a concentration of a specific reactant pretty high. So, next it is the unimolecular second order reaction, which is different from the bimolecular one, and the integrated form is also different. Right. So, what is that? It is, let us say, 2A giving product. So, minus of Ra, which is Ca naught into dxa dt, is equal to k into Ca square, which is k into Ca naught square into 1 minus Xa whole square. So, this dxa by 1 minus Xa whole square equal to k Ca naught t, and here we have to integrate it from 0 to Xa. So, it is 1 divided by 1 minus Xa, minus sign and this minus sign in the derivative will cancel out, and 0 to Xa. So, this is this is d of, with a minus d of 1 minus Xa, then there will be another minus sign. So, 1 divided by 1 minus Xa minus 1. So, it is 1 minus 1. So, Xa divided by 1 minus Xa equal to k Ca naught into t. So, that is the final form. Right. So, if we have linear profile of Xa by 1 minus Xa versus t, so the slope is k into Ca naught, and from there we can calculate the value of k. So, this is the unimolecular second order reaction. An alternative to Xa, we can also go for Ca as well, because you see this is minus of dCA dt is equal to k Ca square. So, minus of dCA divided by Ca square is equal to k into t, integral from Ca naught to Ca. So, it is 1 by Ca after integration including the minus sign. So, 1 by Ca minus 1 by Ca naught equal to k into t. So, instead of going for Xa, if we plot 1 by Ca versus t, and we will get a straight line with non-zero intercept. Right. So, this is 1 by Ca naught, and this slope is equal to k. So, this empirical rate equation for nth order. So, this is nth order reaction. Why we are discussing this, it will be automatically clear. This may be also valid for non-elementary reaction as well, right? Like we have minus or alpha A or AA rather, right? No, alpha A plus beta B giving product, and its rate equation is minus Ra equal to k Ca to the power A, Cb to the power B, etc. Now, if A is not equal to alpha, B is not equal to beta, it is typically non-elementary. Let we have reactants in their stoichiometric ratio. That is, Ca naught by alpha equal to Cb naught by beta is equal to Cc naught by gamma, etc. Therefore, as a depletion taking place in terms of their stoichiometric proportion, so we will have Ca by alpha equal to Cb by beta equal to Cc by gamma, etc. Right. So, Cb beta by alpha Ca, Cc is equal to gamma by alpha Ca, etc. So, minus Ra equal to k Ca to the power A into beta by alpha Ca to the power B into gamma by alpha Ca to the power C. So, we will have k into beta by alpha to the power A, gamma by alpha to the power B, whole bracket into this Ca, A plus B dot dot. So, it is k prime into Ca to the power n, where n is the overall order of the reaction. So, you see that if we have started with the stoichiometric proportion of the reactant, we can reduce this into the nth order reaction. Now, if this nth order reaction, constant volume as it was, if we integrate, then minus of dCA dt, it's k, let's consider it to be k prime or k prime, whatever it is, Ca to the power n. So, minus of dCA divided by Ca to the power n is equal to k prime t, and here it is to be integrated from Ca naught to Ca. So, this is minus Ca 1 minus n by 1 minus n Ca naught to Ca, and we will have this Ca naught to the power 1 minus n minus Ca to the power 1 minus n equal to or Ca, and here Ca naught equal to n minus 1 equal to n minus 1 into k prime into t, right. So, that is the integrated form, or rather this will be negative. So, Ca naught minus Ca, and this is 1 minus n. Whether I have done it correctly, Ca naught to the power Ca to the power 1 minus n, Ca naught to the power 1 minus n, n minus 1 k into t. Fine, and this is valid for k not equal to 1. So, here we will introduce the concept of half-life. So, what is half-life? You have studied it in 10+2 chemistry for radioactivity. What is half-life? So, it is represented as T half. At T is equal to T half, concentration, the present concentration becomes half of the initial concentration. So, Ca naught to the power 1 minus n minus Ca to the power 1 minus n is equal to 1 minus n k prime into t that we have got. So, Ca naught to the power 1 minus n minus Ca naught to the power Ca naught by 2 to the power 1 minus n 1 minus n k prime into t, or T half rather, right. So, T half is equal to Ca naught to the power 1 minus n. So, 0.5 to the power 1 minus n minus 1 divided by n minus 1 into k prime. So, that is the relation. Right. So, that is the relation between the half-life and concentration. Okay. So, you see that from the half-life analysis, evaluation of n from half-life analysis. So, this is the integral approach of directly determining the order. So, what you will do? You plot this log of half-life and log of Ca naught, and this if you get, then 1 minus n is greater than 0. So, n is less than 1. If you get this 1 minus n, the slope is less than 0, n is greater than 1, and if you have this, n is equal to 1. Right. So, this is the approach of half-life by which we can solve for the order of the reaction directly without assuming any model from the integral method of analysis. Right. So, similar to half-life, we can also think of fractional life as well. Like at t equal to T1 by f, Ca equal to Ca naught by f. So, the equation remains the same, only here we will have 1 by f. So, that is the nth order reactions general form and the concept of half-life. Lastly, we will discuss about the zero order reaction. Zero order reaction, we have to be careful about a specific issue. Let me discuss it. Constant volume. So, minus of Ra equal to minus of dCA dt equal to K, right. So, Ca equal to Ca naught minus Kt. Okay. So, if I plot this graph Ca versus T, it must be like this, but here it must stop, it must not continue in this direction because otherwise the concentration is negative. So, we will write for T less than equal to Ca naught by K, and this is equal to 0 for T greater than Ca naught by K. So, that is the only point we have to note. It is typically related to geometry, and from there we can actually get this idea. And you see this Ca naught minus Ca is equal to K into T. So, which means it is Ca naught into Xa equal to K into T. So, Xa is 1, and after that, this Ca naught into Xa. So, if you are plotting Xa versus T, it will be, so Xa is equal to K divided by Ca naught into T for T less than equal to Ca naught by K, and this will be equal to 1 for T greater than Ca naught by K. So, my data will be like this. So, if that happens, it is a zero order reaction, and this is Ca naught by K. Correct? So, that is the overall idea of the zero order reaction. So, next we will go for, so far we have discussed about the single reaction. So, next we will go for multiple reactions. First it is the series reaction. Okay, now it is irreversible reactions in parallel. Say A giving R giving S competitive parallel reaction. This is K1, this is K2. So, you can write that minus of RA, say this is the pathway 1, this is pathway 2. Minus of RA1 is equal to K1CA, which is RR, and minus of RA2 it's equal to K2CA, which is RS, right. So, minus of RA, the overall rate of dissipation of A. So, this is K1 plus K2, K1 plus K2 whole bracket Ca. So, as it is constant volume minus of dCA dt, which is Ca0 into dxa dt is equal to K1 plus K2 into Ca0 into 1 minus Xa. So, the integrated form is minus of ln 1 minus Xa is equal to K1 plus K2 into T, right. So, that is for A, or alternatively we can write this as ln of Ca0 by Ca, because this is ln of 1 divided by 1 minus Xa. So, it is Ca0 by Ca, and that is equal to K1 plus K2 into T. So, you see that if we plot this ln of Ca0 by Ca versus T, and these are the scattered plot. So, from the slope I will get the value of K1 plus K2, but we have to solve for K1 and K2 individually, right. So, for that what is to be done? So, you see RR by RS is equal to dCr dt dCs dt equal to K1 Ca by K2 Ca is equal to K1 by K2. So, dCr by dCs K1 by K2. So, Cr minus Cr0 Cs minus Cs0 equal to K1 by K2. So, if I plot concentration of R and concentration of S here, I am supposed to get scattered plot like from here. So, from the slope we can solve for K1 by K2, right. So, here we are getting K1 by K2, here it is K1 and K2. So, from these two curves we can solve for K1 and K2 separately. But if we think that A giving 2R and A giving 3S and both K1 and K2, so minus RA is again equal to K1 plus K2 Ca, and we can solve as ln of Ca0 by Ca is equal to K1 plus K2 whole bracket T. However, dCr by dCs, just you try to understand that here this is equal to minus of plus of RR and RS. So, this is twice of minus RA1, thrice of minus RA2. So, 2K1 divided by 3K2. So, here the slope changes. Okay. And if I have 2A giving 3R and 5S. Next, it will be minus of Ra, both second order, right, elementary reaction. If we think that it is, what are the variations I am trying to point it out? K1 plus K2 Cs square. So from here we have to get the slope, that is 1 by Ca is minus 1 by Ca naught is equal to K1 plus K2 whole bracket T. So from the graph of 1 by Ca versus T, we have to get the slope of this. And alternatively, you see that Rr by Rs is equal to dCr by dCs is equal to 3 by 2 K1 Cs square, and here 5 by 2 K2 Cs square. So it is 3 by 5 K1 by K2. Right. So these are the variations we can have here. This is given in book, but what I have demonstrated, that's an idea that will give you the idea about how to deal or how to tackle with the stoichiometric heterogeneity, that it's not A giving R but 2A giving 3R, and it's a second order reaction, elementary reaction. So from there, how can solve these, a simple demonstration. Yeah. And before we proceed to the series reaction, let's discuss another one, which is referred as autocatalytic reaction. So what is an autocatalytic reaction? The simplest example, A plus R giving R plus R. That is, one of the reactant is behaving as a catalyst. Right. So minus of dCA dt equal to K1 Ca into Cr. Right. So it is K1 Ca. Now Cr, how do you write? That's the point. Now you see here we have a pretty simple issue, because all the stoichiometric coefficients are 1, and actually it gives A giving R catalyzed by R. So Ca0 plus Cr0 is equal to Ca plus Cr, and initial total number of moles, let it be C naught. So Cr is equal to C naught minus Ca. So that's a technique. So you can write it as C naught minus Ca. Right. So minus of dCA divided by Ca into C naught minus Ca equal to K1 into K1 into simply T, right? And here it is to be integrated from Ca naught to Ca. So 1 by Ca minus 1 by C naught minus Ca. So what you are getting? C naught minus Ca plus this, right? So numerator there will be a C naught. So 1 by C naught will be here. So Ca naught to Ca whole bracket dC. So 1 by C naught ln of Ca by Ca naught minus ln of C naught minus Ca by C naught, right? this is equal to K1 into C naught into T. So, what we are getting finally? Okay, here C naught minus Ca, C naught minus Ca naught, it will be the term, right. So, ln of Ca, C naught minus Ca naught divided by Ca naught, C naught minus Ca, right. Yeah, I have missed the minus sign basically. So, there is a minus, there is a minus, there is a minus, this minus sign will be equivalent. So, ln of Ca naught into C naught minus Ca divided by Ca into C naught minus Ca naught equal to K1 into C naught into T. So, that is the final form. So, if I plot this Ca versus T, right. So, it will be depleting, right, it will be typically depleting. Now, if I want, if I go by an alternative approach, not by using this idea, okay, but by going by this XA concept, so minus of dCA dt is equal to Ca naught into dXA dt is equal to, this is K1 into Ca naught constant volume 1 minus XA into Cr naught plus Ca naught into Xa, because this R is not being consumed, we may think it. So, you see this is K1 into Ca naught square into 1 minus Xa into M plus Xa, just like very similar to the bimolecular second order reaction, but there was a minus sign. So, M is equal to Cr naught by Ca naught, and this is Ca naught into dXA dt, and this Ca naught cancels out. So, dXA divided by 1 minus Xa into M plus Xa integral 0 to Xa is equal to K into Ca naught into T. So, this will give you finally this 1 divided by M plus Xa minus, or what will be that? 1 divided by 1 minus Xa. So, 1 minus Xa minus M minus Xa minus M. So, 1 divided by 1 minus Xa minus M. So, 1 minus M integration 0 to Xa dXA equal to K into Ca naught into T. So, if I integrate it, and now it is pretty simple, right, M 1 minus Xa minus 1, so 1 plus M. So, it will be ln of M into M plus Xa, yeah, it will be ln of M plus Xa divided by M into 1 minus Xa equal to K into Ca naught into 1 plus M into T. So, if I plot from here, if I get this Xa, so Xa, you see, it will be following a sigmoid type of curve, right. It will be following a sigmoid type of curve, and this is 1. It will be approaching towards 1. So, here it is low dXA dt, so low rate. Here initially it is also low dxa dt, low rate, and here the rate is maximum. Now actually if I plot minus of RA versus CA, what I will get? I will get this sort of curve, right. So this is CA equal to CA naught at some position here, the rate is maximum, and the reaction proceeds in this direction, finally going to 0 CA, okay. Finally it goes to 0 CA. Now minus RA, as we have noted, equal to K into CA into C naught minus CA, right. So it is K into CA C naught minus CA squared. So derivative of minus RA dCA is equal to K into C naught minus 2K into CA. So CA star, so CA star when it is C naught by 2, then the rate becomes maximum, right. So autocatalysis will start initially with a low rate, then rate goes to the maximum, then again drops, which is also similarly portrayed by this XA versus T plot, right. So that's all for this session. In the next session, we are going to discuss about the series reaction and first order reversible reaction, differential analysis, and the variable volume concepts, right. And afterwards, we will go for this ideal continuous reactor analysis and their design. Thank you.